today's lecture, we will give you some examples on how to find big O of some functions. Last lecture, we introduced the basic definition of big O, and also we introduced two methods that were used to find big O of polynomials. The first method was based on ad hoc calculations, and the second method was a general procedure to find the values of g of x and the witnesses. So let us solve the first question. For this polynomial, we are going to solve it using the two methods, the ad hoc calculations and using the general procedure. So for the ad hoc calculations, we start by saying for x greater than 1, and then we write the function for x raised to power 5. By the way, there is a typo error. This is supposed to be x not equal to n, and then minus 6x raised to power 4 minus 2x raised to power 3 plus 2x squared plus 1 less than. Now every term, keep this term, the dominant term, as it is, 4x raised to power 5, and now minus 6x raised to power 4 will be replaced by 6x raised to power 5, minus 2x raised to power 3 will be replaced by 2x raised to power 5, and 2x squared will be replaced by 2x raised to power 5, and finally 1 will be replaced by x raised to power 5. Since all the terms have x raised to power 5, we add the constants, the coefficients. So 4 plus 6 is 10, 10 plus 2 is 12, 12 plus 2 is 14, and plus 1 is 15. So here we have 15x raised to power 5. So we say that the g of x is equal x raised to power 5, and the witnesses k is equal to 1 and c is equal to 15. Now by using the general procedure, so there is no need to do the ad hoc calculations. Simply we can say let g of x is the dominant term. And what is the dominant term? It is x raised to power 5. And we say k is equal to 1, and we say c is the addition of the absolute value 4 plus 6, the absolute value of the coefficients. We add them, 4 plus 6 plus 2 plus 2 plus 1, and this is equal to 15, and this will prove that big O of this function belongs to x raised to power 5. Now for the second question, you are given two functions f of n and g of n, and here we want you to prove that f of n is big O of g of n. In this example, suppose you are given two functions, f of n is equal to 3n squared plus 6, and g of n is equal to n raised to power 3 plus n. Prove that f of n is big O of g of n. Here we are going to use the basic definition. Since we have two functions, so all what we need to do to prove it by using the basic definition is to find witnesses c and k. First we write our objective here. So we have our objective. Our objective is to prove that 3n squared plus 6 is less than or equal to c multiplied by n raised to power 3 plus n. So this is our objective, is to find the value of c by suggesting a k at the beginning, and then we find c. So here if you compare left hand side and right hand side, if you multiply these, so you will get cn raised to power 3 plus cn. So I need to replace 3n squared by a constant multiplied by n raised to power 3, and I need to replace 6 by a constant multiplied by cn. So my first trial, first we assume that let's say n is greater than or equal to 1. So in this case, I can say that n square is less than or equal to n raised to power 3. So here n square and here n raised to power 3. Multiply both sides by 3. So 3n square is less than or equal to n raised to power 3. Now for n greater than or equal to 1, also we know that 6 is less than or equal to 6n. So we can start by replacing 3n square, we replace it by 3n raised to power 3, and replace 6 by 6 of n and see whether we can get to the target equation multiplied by c. So we can say that then 3n square plus 6 is less than or equal to 3n raised to power 3 plus 6n. But you know that to get a constant multiplied by n raised to power 3 plus n, then I need to take a common number in here, so that when I take it outside, I will get n raised to power 3 plus n. And here, if you take a 3 common, what you will get? You will get n raised to power 3 plus 2n. And this equation is not the same as this equation. So we can go further. So let me erase this part. Sorry, I need to go back. Let me just erase this part. And now, you know that 6n, I cannot replace it by 3n. So for example, if I want to continue and say that this is a 3n raised to power 3 plus a 3n, why I want to do this? Because if I want to take a 3 common, I want to get n raised to power 3 plus n, and this is what we are looking for. But here, this is wrong. Why this is wrong? Because 6n is not less than or equal to 3n. So I cannot go from this step to this step. My move is wrong. So this is why my replacement for 6 is less than or equal to 6n is wrong. So I need to find an alternative way to get rid of this problem. So I will just simply erase this step because this step is not correct. Now, all what I want to do now, I don't want to replace 6 by 6n. I want to replace it by 3 because you have seen that I have to take a 3 common, and here I have a 3. So I'm going to replace it by 3, a 3n. But in here, when this inequality will be true, this condition is not true. So if you try to solve this inequality, divide both sides by 3. So what you will get n is greater than or equal to 2. So that means this condition is not correct anymore. So now we have, if n greater than or equal to 1, we can replace 3n squared by 3n cubed. But for n greater than or equal to 2, we replace 6 less than or equal to 3n. So what we do? We remove this condition and replace it by n greater than or equal to 2. So now we can say that 3n squared plus 6 is less than 3n raised to power 3 plus 3n, but for all n greater than or equal to 2. Because if this is true for n greater than or equal to 1, so definitely it is true also for n greater than or equal to 2. So we can say that n is greater than or equal to 2. And now here you can take 3 common, and you have reached your conclusion or your objective. C is equal to 3 and K is equal to 2. Notice here I'm using equal, but it doesn't matter. I can replace it by for all. We can also replace it by for all n greater than 2 to comply with our basic definition. For the third example, we need to find the order, which is big O, for the sum of the first n integer. Let us see how we can find this order. First, we need to write the function for the summation of the first n integers. So we write f of n is equal to 1 plus 2 up to n, and n is greater than or equal to 1. We will find the order using the two methods, the ad hoc calculations as well as using the general procedure. So first, we will use the ad hoc calculations, and we start the calculations by saying for n greater than or equal to 1, we have 1 plus 2 up to n is less than or equal to. Now if I replace 1 by n and replace also 2 by n, in other words, replace every term in the summation by n, then we will have this equation on the right hand side. And since you know that as a draft here, you know that 1 is less than n or equal to, 2 less than or equal to n, 3 less than or equal to n, and also n is less than or equal to n. So when I replace 1 by n, then these equations are not equal, it will be smaller. Why? Because this term is smaller than this term, so this whole equation is less than or equal to this whole equation. So how many n do we have here? Since we are adding n numbers, so this is n times. And this is equal to n times n. Let me just write it. N times n, which is equal to n squared. So now we have less than or equal to n squared. So we can say that f of n is less than or equal to n squared for all. Now I will change and I will say for all n greater than 1. Because if the relation holds for n greater than or equal to 1, it should hold for 2, 3, and etc. So no harm, or it will not change the result if I ignore equal in here. So according to the basic definition, we have g of n is equal to n squared, c is equal to 1, and k is equal to 1. So c is 1 and k is equal to 1. So we say that f of n belongs to big O of n squared. Now using the general procedure, so here using the general procedure, remember we apply it on polynomials, so we have to write the function as a polynomial. So you know that f of n is equal to the addition of the two numbers, and this is summation I goes 1 to n of I, and there is a closed form equation for the summation of the first n integers. It is n multiplied by n plus 1 over 2, and this is half n squared plus half n. So this is a polynomial. So for the polynomial, so we can say that f of n is equal to half n squared plus half n. So which term is the dominant term? So this is degree is 2, and the dominant term is equal to n squared. So we can say let g of n is equal to n squared, k is equal to 1, and c will be the addition of the absolute values of the coefficients. So this will be equal to half plus half, and this is equal to 1. And in here we say that f of n belongs to O of n squared. Here by coincidence, we found by the calculations, ad hoc calculations, and using the general procedures, we have found the same constants. But this is not necessarily the case. Maybe by using ad hoc calculations, you get some witnesses, and when you apply the general procedure, you get different witnesses. Put in your mind, recall that the general procedure can be used only for polynomials. For other functions than polynomial, you cannot apply it. Now, for example number 4, the function we have is not polynomial, so therefore we cannot use the general procedure to get the values of g of n and the constants. So we need to use ad hoc calculations for this particular function. So we will start the proof by assuming a value for n. But before that, we need to ask the following question. If n is greater than 1, so which one is smaller or greater than the other one? Is 1 over n plus 1 greater than 1 over n or less than or equal to? By taking an example, let's say n is equal to 2. So if n is equal to 2, so what you will have? You will have 1 over 3 and you will have 1 over 2. So which one? So this is 0.5, this is 0.333. So which one is larger? The larger is half, so we say that this one is less than but not equal, it is less than. So that means that this is less than, and we will put equal here. So we have for n greater than 1, we have this inequality. At the same time, if I want to compare log 2 of n with n, so which one is smaller and which one is greater for n greater than 1? The answer is that log n is less than or equal to n. And of course, this one needs a proof also, but we will use it here, okay, without a proof. Again, we will ask ourselves log 2n and n square. Which one is less than the other one? Log 2n is less than or equal to n square. We will solve this question by the ad hoc calculations. We cannot use the general procedure because this is not a polynomial. So let me show you first how we have the first solution in the ad hoc calculations. We will have n square, so we will say n square plus log 2n over n plus 1 less than or equal to, I will keep in the numerator the equations as they are, but in the denominator I will just keep n. Remember that 1 over n plus 1 is less than or equal to 1 over n, so we will ignore 1, and this equation will be less than or equal to this equation. And this is true for n greater than 1. Now for the log, I can replace it either by n or n square. So let me replace it by n, for example. And so if you replace it by n, so you will have here n. And again, if log 2n is less than n, so we will have the inequality less than or equal to n greater than 1. Now here you can take n common plus 1, and then you will divide both sides, and here you will get n plus 1. So our equation is n plus 1. Also 1, see here, 1 is less than n. So I can replace, this will be less than n plus n, and this is equal to 2n. So we can say that f of n is less than or equal to 2n for all n greater than 1. So we have g of n is equal to n, c is equal to 2, and k is equal to 1. The second approach, what I will do, first let me write the equation, n square plus log 2n over n plus 1. I will remove 1 from the denominator and leave n, and also I will replace log by n square. So what you will have here you will have 2n square over n, so you will have 2n, and we will get the same solution as before. We have g of n is equal to n, c is equal to 2, and k is equal to 1. And the third approach, n square plus log 2n over n plus 1, I will keep the denominator as it is. I'm not going to change it, but I'm going to replace log by n. And here when you take n common, so you will have n plus 1 over n plus 1. These will go together, so this is equal to 1. So here we have g of n is equal to n, and c is equal to 1, and k is equal to 1, so we have different witnesses. So in the ad hoc calculations, we don't have one answer and we don't have one approach. We can have many approaches to get to the solution. For the last example, the purpose of this example to show you how to use the basic definition to prove that a function is not big O of another function. In this example, we have two polynomials, one polynomial of degree 2 and another one is polynomial of degree 3. So definitely 7x squared is big O of x raised to power 3 because the polynomial with higher degree is an upper bound to the polynomial of smaller degree. But on the other hand, a polynomial of higher degree is never upper bound of a polynomial of lower degree. So how to prove that x raised to power 3 is not big O of 7x squared using the basic definition? So the first part, show that 7x squared belongs to big O of x raised to power 3. In other words, find two witnesses in the basic definition. So when we write, so for x greater than or equal to 1, we can just say simply greater than. You know that 7x squared is less than or equal to 7x raised to power 3. So this is the value of c. So we say that c is equal to 7 and k is equal to 1. So therefore 7x squared belongs to big O of x raised to power 3. Now to prove the reverse is not true, so show that x raised to power 3 does not belong to big O of 7x squared. Remember that for inside order, we should not have a constant 7. But for just demonstrate the idea of how to prove that a function is not a member of big O of other function, it is included here. We will prove this statement by contradiction. So we say by contradiction, suppose not. And when we suppose not, it means we have to take the negation of this statement. So here we say suppose that x raised to power 3 belongs to big O of 7x squared. Since it belongs to big O of 7x squared, so according to the basic definition, we have x3 less than or equal to a constant c multiplied by x squared for all x greater than k. Here we say suppose that x is positive. Then divide both sides by x squared. So when you divide this by x squared, you divide this by x squared. So what you will get x is less than or equal to 7c for all x greater than k. Here we are looking for something that is not correct, logically incorrect, for the purpose of proving this statement by contradiction. This statement, the final statement we have obtained, whatever the value of c and k, you will see that this statement is not always true. Imagine, for example, you choose c, let's say equal to 1. And also suppose that k is also equal to 1. So this inequality will become x less than or equal to 7 for all x greater than 1. But this statement is not always true for x greater than or equal to 1. Imagine, for example, that x is equal to 8. So if x is equal to 8, this statement is false because 8 is not less than or equal to 7. Also for 9, 10, and 11. So in general, this statement is not always true, this statement in here, is not and always true, and here we will say, but this statement is not true for x greater than the maximum between 7c and k. So you take a value that is maximum between these two, it will make this statement as false. So we have picked the value of c1 and we picked k is 1. So the maximum between 7 and 1, so any value greater than 7 will make this statement is false. Also, if k is equal to, let's say if c is 2, so and k is 1, so 7 by 2 is 14. So any x greater than 14 will make this statement false, and the inequality is incorrect. And this gives us a proof by contradiction that this statement is not correct. So this statement is correct, and this statement is not correct. From this example, we can prove that if f belongs to big O of g, and here I'm ignoring the input of the functions, then it is not necessarily true that the opposite is true by switching the functions, that g belongs to big O of f. Although for some examples it is true, this is why I'm saying not necessarily true. For example, if we have f of n is equal to 3n squared plus 7 and g of n is equal to 6n squared plus n plus 2. Both of them are polynomials of degree 2. Here we have f belongs to big O of g, and we can prove it by using the basic definition. And at the same time, g belongs to big O of f. Also, we can prove it by the basic definition. If we have this situation that f belongs to big O of g and g belongs to big O of f, later we will define a new symbol. We can say that also that f belongs to big theta of g. So big theta, it means that if you switch the functions, then both big O's are true.